Hello everyone, we are group starting and our project is agent-based analysis of rental housing market mechanisms and rental coefficients. The first topic we will talk about is the project's introduction. So when we study the rental market is a complex system that reflects the impact of economic, social complex implications and housing affordability of each individual customers. When economy grows, employment rates and income levels can impact the rental market. During periods of economy expansion, there is often increased demand for rental properties as more people enter the workforce or seek temporary housing options. Changes in demographics such as population growth, aging populations, or shifting household size can impact the rental market. Meanwhile, increasing preference for urban living, flexible housing options, or common living arrangements can lead to higher demand for housing in urban areas or for specific tempos for rental properties. The affordability of rental housing is crucial for both tenants and property owners. Economic conditions such as inflation and changes in income levels can affect affordability. If rental price rise faster than incomes, it can lead to decreased affordability and potential challenge for tenants. So we adopt the agent-based land market model. Its capacity to account for human decision-making influence on land using a mechanical form and especially explicit manner, incorporating social interaction, adaptation, and decision-making at many levels. We know ALMA provides more accurate simulations than traditional API model, since it's based on spatial data economy analysis and especially explicit consideration. And we referenced Wolf and Shift model. We let renter search for a satisfactory listing in the map, like Shift search for food in this model. Okay, this is section 1.
Section 2 is model proposal. Several key assumptions are made in our model. The first one is representation of rental price by the rental coefficient. This coefficient represents the rental price for a specific location comprehensively, considering various elements that may influence rental pricing across different regions while assuming a consistent base value for all properties. The second one is impact of supply-demand relationship on rental price. Number of houses and renters in the grid affect its rental price. So the price is equal to significant level plus demand effect. The third one is renters' preferences. They always wish to find better location and in a lower price. So that means they prefer living in area with higher significant level and lower coefficient. There are two main types of agents are considered in the model, renter and house. For renter, the expect value E representing the max value the building needs to pay. The tolerance coefficient T representing the additional bargaining power when faced with a better house but beyond their budget. Both E and T are normal distributed and they will match friendly, like maybe a renter has a relatively low aspect value but higher tolerance than others. The position is in 2D represents the location of the rental property in the grid. For house, all houses in the same area have the same coefficient value as their price. At the same time, each area has the same number of houses available for deal initially. For the environment, the map, it is built up by 20 by 20 grid. Each grid has multiple houses with the same price, with each cell having an initial rental coefficient of 1. Each cell has a significance level initially equal to its rental coefficient value, guiding the renters' movement towards the most suitable plot based on their preferences and the willingness to pay. Higher the significant level means houses in this area are more popular. There is one center with rental coefficient 2 and two subcenters with rental coefficient 1.6. They reduce the radiation in the surrounding area by 0.1. Coefficient is represented as price, since it equals to initial significant level plus the demand effect. The model mechanism is consisting of operating law of rental coefficient, movement, iteration, and determination. The operating law of rental coefficient is following this equation that the grid coefficient is equal to significant level plus number of renters in the grid over number of available houses in the grid. Once a house is due, the total number of the houses in the grid will be decreased by 1. The movement of renter is following this mechanism in this figure. Check if the price of the grid with a higher level of significance is lower than expect value plus tolerance coefficient. If it is, move to the grid with a higher level of significance. If not, proceed to step 2. The renter search for the grid with same significance level as the current grid and the lowest price, and move to that grid. If the current grid already has the lowest price within the same significance level, proceed to step 3. For the current grid is evaluate as follows. If the current grid price is larger than expect value plus tolerance coefficient, move The model computes the new coefficients iteratively before guiding tenants' movements based on interaction rules. The process terminates when all tenants are matched or a predetermined percentage of tenants have been found. Subsequently, the average rental coefficient of transactions in each area is calculated to offer insights into market dynamics and housing affordability.
Section 3. In Section 3, we're going to display on our model. Okay, this is our model interface. Firstly, we see our map. We have 3 downtown in the map. The central grid of the red downtown has a significant level of 2, and the 2 blue center is 1.6. Those other brown grid is a normal area which has the lowest significant level, which is 1. Each grid has 20 houses for renting. Those black points are renters. They will move under their own movement rules, which we explain in section 2.4. The price of the coefficient value of each point will change when the supply and the demand the relationship change. So renter must search their best houses under acceptable price every turn. Once they make a deal, they will turn to green. Yes, and we have a lot of buttons here. We can set the number of renters in the map, and we can also set their expect value and tolerance mean and standard deviation to fit a better normalize or find a better distribution. Also, we plot the deal. We also will plot and show how many persons have deal and how many persons still finding. And we'll record every due. We will record every precision for new due and new price, and we will output data, and we can find all the due price and the due precision, so we can do a much further analysis for it. Let's move to final section for our presentation. In this section, we will analyze our model's result and discuss its advantage and limitations. First, move to the result analysis. We export the record transaction information during several simulations and find 3 interesting results. First, our model is highly sensitive to the values of renters E and T. It means whether extreme high or low distribution of renters expat or tolerance would make a significant difference outcome. It is essential to find accurate value for simulation under different environment. Second, the final average due price for an area always get the same distribution of its significant level. It means that a house with a higher significant level always deal in a higher average price. Last, our model shows that while supply and demand effect can cause short-term fluctuation in price, the intrinsic value of the house, which is the significant level, remains a critical long-term factor. Our model has several advantages and we conclude into 4. First, our model focuses analysis of supply and demand dynamic. It allows better understanding for rental market and the factor that influence renters' preference. Second, our model simulates the natural human behavior of hesitating when faced multiple choice, providing a more realistic behavior in rental market. Third, we apply the rental coefficient. This coefficient simplify the model and allow us to focus on the critical factor that impact rental price without getting bogging down the unnecessary complexity. The last thing is by offering the different input, our model can adapt to different scenario and more accurately simulate the rental market. It's very flexible. But also we got 3 limitations. The first limitation is our model generates unrealistic house distribution. We assume that every area has the same number of the house at the same time. This potentially swing the result and reduce the reliability for our finding. The second is the iteration efficiency. The model's iterations can be time consuming and very time wasting, which could limit its application in a large input or in a more difficult market. The last limitation is we ignore the difference between the house. Our model failed to account for unique character for individual house. We just assume that the house in the same area has the same price, has the same character. In conclusion, our model offers a variable insight into the rental house market, capturing the interplay between supply and demand and simulating the realistic rental behavior. However, it does have some limitations, such as unreasonable distribution for house, inefficient iteration, and ignoring the difference between the houses. We hope that the future research can adjust this limitation and the future improve them. Thank you for your attending, and our presentation is over now.